Hello, thank you everybody for coming to this talk and welcome to AtScale. My name is Jitu Padhe and I'm going to present work on Microsoft's large-scale RDMA deployment. I've been at Microsoft for 20 years. I've done many things and I'm presenting this on behalf of a very large team. So this is work of many, many people that I'm presenting here. Okay, so with that, let's launch into the talk. First and foremost, this is a high-level overview. I'm going to start with a very brief one-slide summary of what we have accomplished. Then I'll give you an overview of how we deployed RDMA at scale in Azure, what the challenges were, and one of its core technical components, the data center QCN, congestion control algorithm. Okay, so if all you remember for this presentation is this one slide, these are the 4 points I want you to take home. RDMA is a technology that transfers data between servers without burning CPU cores. We in Azure use RDMA for storage-related traffic. So when VMs mount disks, these disks transfer data from storage clusters to compute clusters using RDMA. Over 65% of our traffic, 65% in Azure DCs is now over RDMA. And some of this traffic goes over 100-kilometer links. This is what I mean by scale. This scale is made possible by many innovations. One of them that I'm going to talk about a little bit today is Data Center QCN. This is our congestion control algorithm. And why do we do all this? Obviously, we do it because it reduces cost of goods sold, the COGS. It improves latency and jitter for our end users. And RDMA is absolutely critical for many of the high performance workloads that we enable in Azure. So what is RDMA? RDMA is essentially remote direct memory access. Now, many of you may not be familiar with this term, but you are definitely familiar with the second half of the term, DMA. This is direct memory access. It's a way to transfer memory from peripheral to CPU to the memory without burning CPU. So typically, this is used for transfers from network cards or disks directly into the memory without hitting the general purpose CPU. RDMA, so essentially remote DMA, allows you to use the same idea, except now you're transferring data from server to server without burning cores. Now, here is why this matters. So let's imagine a very simple application. Take a block of data and move it from remote disk A to local disk W, from address X to remote disk Y, address C. Okay. If you were to use TCP, this is how this application works. The application prepares a buffer of data called send. TCP/IP, which is now CPU, is going to packetize the data. It's going to transfer it over the NICs. Now that transfer is DMA, but that's kind of not the issue here. The data goes over the wire. At the receiver end, again, the NIC is going to interrupt as the packets come in. The TCP/IP stack on the receiver is going to pick it up. It's going to put it to the application buffer. There's a copy involved. All of these steps are burning a bunch of CPU. Now, obviously, TCP/IP is a fairly heavyweight congestion control algorithm, so ACKs are coming back, and you're going to see a number of problems. So TCP essentially is spending a lot of CPU, and in addition, because you are transferring to kernel and transferring between the application and the kernel boundary all the time, you see high latency. RDMA, on the other hand, bypasses all this. Application prepares a buffer, publishes it to its NIC, saying, hey, here is a certain amount of buffer, certain amount of memory that I'm going to allow other applications to read. The reader tells its NIC, here is my buffer, and go copy that particular buffer from that particular IP address, and here is the virtual address of where that remote buffer is. The two NICs handle all the packetization, congestion control, retransmission, whatever it may be, and the data simply is transferred between the NICs. The NIC puts it in the application's pre-recorded buffer on the receiver side. Once the data transfer is complete, the NIC rings the doorbell, and only then the receiver application moves. So basically, you move data from sender to receiver entirely using NICs. The CPUs of the two sides are not involved at all until it's time to simply pick up the ready buffer. So this is why RDMA is attractive for us. Essentially, avoids burning CPU. Okay. The benefits of RDMA, simply to reiterate them, it's essentially offload. They come from offload because we are going to get very high throughput, over 50 Gbps with very negligible CPU overhead, both on the sender and the receiver side. And then, since we have offloaded, because we have kernel bypass, it also enables low latency and low jitter. Oftentimes, what you will see that people will think of DPDK and other kernel bypass technologies in the same breath as RDMA. That's useful because they are a kernel bypass technology. But remember what DPDK doesn't offer you. DPDK is not going to reduce your CPU cores. In fact, DPDK will consume a certain number of CPU cores, run a tight loop, process packets that way. Okay, so it doesn't offer the benefits of offload. So it will offer you kernel bypass, will offer you high throughput, but you'll burn cores. If you're a public cloud provider, you do not want to burn cores because that's your primary business. This is why RDMA is important to us. So the RDMA deployment in Azure, here is a rough overview of what it looks like. There are two primary applications, if you will, or two primary scenarios in which we use RDMA. One is traffic within our storage clusters. That's shown at the top. We have a storage cluster. These are a bunch of servers with large number of disks. They connect to a cluster fabric. It's a standard class fabric. We've written many papers about this. And within this cluster, the longest cable is about 100 meters. By the way, if you're wondering why I'm talking about the cable length, come back to that later. So this is a fairly quote unquote small deployment. There is maybe about 20 to 30 racks worth of machines, not that many more. They all connect to cluster fabric and we are transferring data between them. The second one is when the VM mounts the disk. When the VM mounts the disk, that transfer between the compute cluster and the storage cluster, it's the VHD read and write traffic. That also goes on. Now, the compute cluster and the storage clusters might be in the same data center. Sometimes they are not in the same data center. So they go over what we call our DC and regional network gateway. In this fabric, the largest link can be up to 100 kilometers because you're going between different data centers. And this is where some of the TCQCN's technological achievements shown through. Okay, so again, we use RDMA within a storage cluster, and this is essentially disk replication traffic. When a write comes from the VHD side, it's replicated multiple times. When a disk is full, we basically break it apart and do erasure coding. When the disk fails, we carry the replica. All of that traffic is on RDMA. We call it essentially the storage backend traffic. That's shown at the top. And at the bottom is what we call the front-end traffic. When the VMs mount the VHDs, the transfer between the VMs and the storage cluster is also going RDMA. Okay, so essentially the entire storage stack is using RDMA. Okay, and this is essentially the dominant traffic in any public cloud. It is also the dominant traffic in Azure. Our scale is vast, over 10 to the 19, that's exabytes per day. And we have over a trillion IOs per day that are all going over RDMA. I'll come back to this point later. We believe that we are quite possibly the world's largest deployment of RDMA technology. Now, this is essentially a networking conference. There were many challenges in the system side, but what were the primary networking challenges? The primary networking challenge here was to go from InfiniBand to commodity Ethernet. Now, as many of you know, RDMA is not a new technology. It's been around since maybe even late 90s. However, back then, RDMA was primarily used on specialized InfiniBand hardware. These were essentially completely specialized stacks from L1 to L7. Can't really do that in a public cloud. I mean, we have an InfiniBand deployment. It's not that we don't have it, but you can't do it at scale. It's not cost effective. It's not cost effective to use InfiniBand to transfer data between compute and storage, or even within storage. That's just can't afford to maintain two stacks. Commodity Ethernet is the way to go. So the main challenge here was to go from InfiniBand to commodity Ethernet. All of the RDMA deployments before we started were maybe 1,000 nodes, 2,000 nodes. I remember looking up the literature. Maybe 10K. I remember one maybe, right? But we had to go to 100K, 100,000 nodes more. Essentially, all of Azure's VM traffic. How did we do that? Basically, we went for what's called RoCE, RDMA over Converged Ethernet v2. We love to make acronyms, so this is a big acronym. This essentially takes an InfiniBand layer 4 packet and puts it into a UDP packet that goes over standard Ethernet IP stack. Now, why do we do that? UDP essentially provides us the standard entropy that's needed to spray our connections, ECMP. And InfiniBand allows us to use the standard InfiniBand transport protocol. There's a hitch though. The InfiniBand L4 assumes, because it was developed for the original specialized InfiniBand hardware stack, InfiniBand assumes that the underlying fabric is lossless. Lossless, now, come to think of it, this is a term that we all use. Lossless is kind of a bad word. There is no such thing as a lossless fabric because packets are always going to drop because you might have CRC errors or whatnot. However, what we need is a fabric that is drop free, which means there are no congestion induced drops. Why? Because that allows us to start fast. You can start transmitting, unlike TCP slow start that many of you are here with. It allows you to start at line rate. Also, if there is no congestion drop, it means there won't be retransmission because of congestion. Now, you still might have CRC errors, and you take pains to keep CRC errors in our network low, but you won't have retransmissions. How do you do this? Standard Ethernet offers nothing in this regard. However, there is a technology, 802.11qBB, priority flow control, that allows us to make Ethernet lossless. Again, remember, lossless means simply drop free of congestion. And how does this technology work? And this is essentially the key technology for that allowed us to go from InfiniBand to commodity Ethernet, RoCE V2. So how does the PFC work? Here is how this works. Essentially, when router's queue starts filling up, it tells the upstream router, please stop. And now you have to do this obviously before the queue completely fills up. There is a little concept of headroom. But setting that aside, that's the basic idea. My queue is filling up. I tell my upstream neighbor, please stop sending to me until my queue clears up. And then you go. This is accomplished with a pause frame. And here is a little animation. This is how it works. So the blue flow is going to get congested and buffer starts piling up. Let's say our PFC threshold, pause threshold is 3 packets, at which point this router tells the upstream router, please pause. So at this point, any further blue packets that come into the queue stay put at the upstream router. They don't go further down to the second router, and we continue like that. The key thing to note here is look what happened to the green packets. There are 8 different queues. Most ASICs support the 802.11qBB standard allows for 8 priorities, and most ASICs support that today, the commodity silicon ASICs. Pause is on a per queue basis. We reserve 2 priorities in Microsoft for our RDMA traffic, 3 and 4, just happens to be the ones we picked. Pause on one priority does not affect traffic on other priorities. So if you put your TCP traffic on the green side, just because your RDMA traffic is paused, doesn't do anything worse. This is very different from the original notion of global pause. Global pause means please stop sending everything. That's dangerous because congestion on one queue is going to affect all queues. Here it allows us to separate RDMA traffic from TCP. So this is sort of the brief idea of behind RoCE V2. So UDP header and lossless Ethernet, that is what allowed us to scale from InfiniBand to general Ethernet. Okay, so the problem, however, is PFC is troublesome in large deployments. And why is that? These problems are well known, by the way. There are many, many papers. I'm just going to give here an overview. One of the problems is so-called victim flow. What is a victim flow problem? Here is what happens. Imagine that you have these flows going through. So you have a blue flow, a green flow, and a purple flow. Now look what's happening. These 3 flows are going from H1, H2, H3. They're going to the receiver R. The bottleneck link is very clear. The bottleneck link is from the last switch down going to receiver R, where all 3 flows are going. If these are 40 gig links, we are going to expect these flows H1, H2, and H3 to get roughly 1/3. That's what happens. RDMA, TCP doesn't matter. This is what you roughly get. Great. Now imagine a second flow that goes between S and D. If you start this flow, and if you're running TCP, what do you expect? The bottleneck link here is the link where the blue and red flows are traveling together. And we already know that the blue flow is eating up 13.3, so the red flow should be able to get the rest of it, which means it should get roughly 26.6. What happens, unfortunately, is with RDMA, standard RoCE deployment, is it gets only 13.3. So 50% of the bandwidth remains unaccounted for. Why does this happen? This happens because pauses operate on a per port basis instead of a per flow basis. So think about what happens when a pause starts flow. R is getting too much traffic, so it tells the switch, please stop. The switch then tells the blue flow to pause, right? And these pauses cascade down. and the blue flow is paused. Note, however, what happens at step 4. At step 4, you're telling both blue and red flows to pause because the pauses are on a per port basis instead of a flow level. So the little red circle with the number 4, that's pausing both red flow and blue flow, and it's pausing them equally. As a result, both flows get the same throughput. This is bad because the red flow has nothing to do with the congestion at the receiver, and yet the poor flow is getting victimized. Okay, so red flow is victimized, and that's what we want to avoid. What is the solution? The most naive solution is using one priority per flow. Can't do that, right? As I said, most ASIC supports only 8 queues. The 811 QBB standard support 8 flows. There are ways to maybe get around it. Maybe we can use fancy DSCP values and stuff like that, but nah, not really. So our idea is very simple. We're going to build a per flow congestion control algorithm and use PFC as our last resort. PFC is our 911 call. We don't want to get rid of PFC because we do need lossless Ethernet because that's how the InfiniBand L4 works the best. That's what allows us to build a very, very simple congestion control protocol and not deal with things like slow start and allows us to do ACK consolidation and so forth. But we want to avoid this victim flow problem. So what we want to do is do per flow congestion control whenever possible and use PFC only as a last resort. And this is where the congestion control protocol comes in. We built it. This data center QCN, DC QCN. This is a joint work between Microsoft and Mellanox. And this is used not just by Microsoft, but many other companies as well. So this is per flow congestion control, and we use ECN for this. I won't go into the details of DC QCN. We have multiple papers out on this topic. But at a very high level, this is what it looks like. Using the standard IEEE terminology, there is a reaction point, there is a congestion point, and there is a notification point. In other words, there is a sender, there is a router, and there is a receiver. The router, which is the congestion point, which is where congestion happens, it marks ECNs based on queue lengths. The notification point, which is essentially just the fancy way of saying receiver, it reflects this ECN marks based using special packets called CNP. And the reaction point, which is the sender, takes in these CNPs and it adjusts its rate based on what we get. Okay, so this is very much similar to TCP and ECN. Many of you are familiar with that. Maybe tomorrow Quick will start using it too. The router marks ECN, TCP acts reflected back, and the TCP sender, using whatever algorithm it's using, adjusts its sending. Okay, so this is very much similar to that. The only difference here is that CNPs are special packets, and the rate adjustment algorithm is specifically tuned for certain aspects of RDMA. This, however, is easier said than done. And why is that? That's because there are 3 big elephants in the room. Number 1, we have to tune the router buffer, and I'll tell you why that in a minute. We have to tune DCQCN parameters. This, of course, is not unique to DCQCN. Any congestion control algorithm has many, many parameters, and they need to be tuned. And then, of course, this is all theory. Ultimately, there is dirty work to be done, and we'll talk about that a little bit. So, what's the issue with the router buffer tuning? The idea here is that routers need to mark ECN before they fire PFC. That's obvious, right? If a router started firing PFCs before ECN, then why did we even have DCQCN? It's not going to do anything. However, notice what the problem is. ECN is marked on egress, while PFC is marked based on ingress. So imagine this packet's coming in. There's a single port that's sending traffic to 3 different flows. And let's say we have basically a bunch of traffic that's pending, right? So each of the egress ports, 2, 3, and 4, have 2 packets pending each. And Q1, which is where all the packets came from, that essentially, now you can say that the ingress queue is 6, and the egress queue on all the other ports 2, 3, and 4, that's just limited to 2. Why is this a problem? Because think about this. When you mark ECN, that's marked on egress, which means you have to count when you decide what threshold to mark ECN at, you have to look at the queues on the egress side. PFC, on the other hand, is marked on the ingress side, so you have to look at number 6. For this simple scenario, the calculation is very simple. ECN should be less than 2, PFC should be more than 6. That's the answer, right? That will guarantee you that in this particular case, you will always mark ECN before you send PFC. But this calculation is non-trivial for the general case. And there is a lot of detail that's in our DCQCN paper that we published in SIGCOMM. This is the primary work we had to do. Unfortunately, this work has to be done for every ACP on board. We have now established a way to do these calculations with our router vendors. And that's what allows us to mark the ECN and buffer settings. I already talked about memory tuning, and now we're going to talk about parameter tuning. Like any congestion control algorithm, DCQCN has many, many parameters, and tuning that is one of our biggest challenges. So what did we do? This is where a little bit of math muscle came in. We built a very, very accurate fluid model, what the algorithm was. Here is a component, these are the differential equations. The top one captures rate decrease due to ECN. The second part of the equation captures essentially what we call byte counter rate increase. And the last one captures a time-based component or timer-based rate increase. So it's a partial differential equation. Based on that, we can decide how the algorithm would convert for various settings of the parameters, the primary there being alpha, as well as the various rate increase thresholds, RT and RC. And given this sort of accurate fluid model, and you have to multiply this by n flows, so there is a system of differential equations. And what we found, and actually we tuned this until our implementation matched our fluid model very carefully. Once we had the fluid model, we used it in a standard parameter sweep study that allowed us to find the sweet spots for capturing the performance of the DCQCN algorithm. And this model is what gives us confidence that when we deploy it on large scale, on long 100-kilometer links and so forth, it will work beautifully. So this is the thing. Now, of course, there are many, many issues, and there are many war stories I can tell you. And, for example, DCQCN had to deal with quiescent flows. Everybody develops congestion control algorithms for long-lived flows that are continuously transmitting data, so-called greedy flows. That's not how the world looks like. In practice, your disk traffic is on, off, on, off. You have to deal with that. There are numerous hardware and interop issues. And the reason of this, of course, was we were the first people doing it. Microsoft was the first company doing it at a giant scale. We had to deal with multiple vendors, and there were all sorts of problems with that. Coexistence with TCP. Now, remember the blue and green flows? That's solved. We put TCP on a different priority, so coexistence with TCP, classic bane of all congestion control algorithms, non-issue, thankfully. One thing we learned out of this whole thing, and this is not so much DCQCN specific as it's RDMA specific, is once you enable, RDMA becomes non-negotiable because it saves CPU and the developers use up that CPU for something else. Okay, so once you deploy RDMA, fallback to TCP, which does chew up CPU, becomes very difficult. So we learned this lesson in a rather hard way and very fast. You deploy RDMA, you don't have a fallback. Okay, it has to work. And then there are many other standard engineering things. We had to enable end-to-end telemetry, alerting, mitigation. So we developed something akin to TCP eStats that many of you are familiar with. We call it RDMA eStats. There is PFC watchdog, which allows us to get rid of deadlocks. There is a whole bunch of things. We have written, again, papers about this. So this is sort of the practical side on top of the theory. When you have DCQCN, by the way, PFCs are nearly non-existent in our network. They do happen, especially when there is bursty traffic, but otherwise, by factors of tens of thousands, there is a difference between PFCs in a non-DCQCN network versus a DCQCN-enabled network. So what comes next? Today, we primarily use RDMA for storage traffic. We're going to do many other things with it. For example, well, actually, I probably shouldn't mention many of those things, but you will hear announcements from us, RDMA, or many more scenarios. We'll be doing innovation about the Rocky protocol itself with our own SmartNIC. Again, this is something that we have written papers about. We will innovate in terms of buffer management, telemetry, and alerting with SONiC. That's our switch operating system. Again, something that many of you guys are familiar with. So we are looking forward to innovating both at the protocol level as well as the switch level, NIC level as well as the switch level, and coupled with enabling RDMA for many more scenarios. So in conclusion, Microsoft Azure arguably has the world's largest RDMA deployment. It was made possible by many technical innovations, including DCQCN that I talked about here briefly today. And it's essentially a culmination of work of solid theoretical underpinnings that came out of Microsoft research, coupled with engineering excellence from our engineering teams. So that's the sum total. Thank you.